Okay, so for this problem, we want to find a general solution for a one-dimensional Laplace equation given the following geometries. So our Laplacian is simply our second derivative of our potential equal to 0. Now for part A, we're given spherical geometry. So we need to know the Laplacian in spherical coordinates, which is often given to you. You can derive it if you want, but it's very long. And the in spherical coordinates, which is what we have, it's 1 over r squared, the partial derivative with respect to r squared, partial of our potential with respect to r, plus there's some other terms here as well, but they all include either dv d phi or dv d theta. And notice that our potential is a function in regards to the radius. So we only care about the radial portion, so we don't need to include all these. Okay, so now what we need to do is we're just looking at the Laplacian of our potential is 1 over r squared. Now it's no longer a partial derivative, it's really just an ordinary derivative. R squared dv dr equal to 0. So we want this to be equal to 0. And if we look at this part here, if we're taking the derivative of a constant, meaning if inside our derivative is a constant, let me highlight that a little bit better. If this right here is a constant, and we take the derivative of that constant, we're going to get a 0. So to find out where this works, we can say r squared dv dr equals a constant, which I'll call c1. Well, now we can simply divide over by r squared, and we can get dv dr is c1 over r squared. Or if we multiply both sides by dr, you get dv is equal to c1 over r squared dr. And if we integrate both sides, then what we find is our potential V is equal to negative c1 over r. And then when we integrate, we get another arbitrary constant, which I'll call c2. And this is our potential as a function of r, and this is just a general solution. Okay. The second one gives cylindrical coordinates. So with cylindrical geometry, it's the same thing as before. When we're looking for the Laplacian of our potential, we're not interested in all the other parts. We're only interested in the part that is phi dependence. So in that case, this will be equal to 1 over s squared, the second derivative of our potential with respect to phi, And this has to be equal to 0. Okay? So what that tells us is, just like before, using the same reasoning, 1 over s squared dv d phi should equal a constant, which I'll call c3. Because if I do a second derivative, if that's equal to a constant and then I take another derivative of it, that's going to get me 0. So we need to solve for this, and you'll get dv is s squared c3 d phi. And again, we can integrate both sides, and you'll get your potential as a function of phi is what? Well, we're going to get a phi added onto there. So we're going to get s squared c3 times phi plus another constant we'll call c4. which just comes, that's the constant of integration. Now for C, it's also cylindrical, but now the only dependence is S. So we're only concerned with anything that's S dependent. So the Laplacian of our potential is then 1 over S. It's just, in one dimension, it's just a normal derivative, d by ds of S dv ds. And this needs to equal 0. And essentially what that means is like before, that S dv ds should equal a constant, which I'll call C5. Then dv is 1 over S C5 ds, and solving for a potential, v as a function of S is C5, 1 over S, the integral of that is natural log of S, plus C6, another arbitrary constant. So those are the Laplacian for those particular areas. And then in the last one, they give us initial conditions, which is find the potential if v of 10 equals 0 and v of 1 is equal to 10. And that's for part C. Well, let's start with when v of 1 equals 10. So that means our S is equal to 1. So you get, and our v is equal to 10, S is equal to 1. That's what that means. So 10 equals C5 natural log of 1 plus C6. But the natural log of 1 is 0. So this is all 0. So that tells us our constant C6 is equal to 10. So I can plug that right into there. So our potential as a function of S is this constant C5, the natural log of the absolute value of S, plus 10. Okay? And now we can use the other condition, which is V10 equals 0. So 0 equals C5, the natural log of 10, plus 10, and then solving for C5, we see C5 is negative 10 divided by the natural log of 10. And we can plug that into here. And finally, we get our potential as a function of x is negative 10, the natural log of s, over the natural log of 10 plus 10. So using these initial conditions, we're able to find our VS. So pretty straightforward problem, not too bad.